Welcome, everyone. Thank you so much for having me. Thank you for the introduction. I will do a little bit more introduction and then we can get started. So the first thing is that this is the first talk that I'm gonna, or like, presentation thing that I'm gonna do where I use live books, because I gotta like use this for some things and I couldn't figure out the use case for quite a while. And then this is like a pretty good one, because I'm not going to do any live coding because that's awkward and never goes right, but we're still going to have code that we can execute. So hopefully that's gonna be fun. So a little bit about myself. I am Andrea. I'm a member of the Elixir core team. I've been in the core team for 6 years now, so quite a long time. I joined around maybe Elixir 1.1 or 1.2, somewhere around there. And it's been a while. I do also a lot of maintenance of open source libraries in the Elixir community, like Redis driver and property-based testing libraries, stream data. There's a bunch of other stuff. I try to put a lot of time in the community ecosystem more than community aspect of Elixir. I'm starting to talk a little bit more on Twitter about what we do in the core team. So if you want to follow me, this is my Twitter handle. I'm sure it's going to be shared by Elixir Kenny as well. So just trying to get followers any way I can. This is our life now. I also wrote a book together with a former coworker called Testing Elixir, which is about, as you might guess, testing stuff with Elixir. There's not a single test in this presentation, so that's where the testing part ends. So what are we talking about? Did I forget anything? Yeah, no, as we said, I'm working at Apple right now. I've been working here for about 5 months using Elixir, which is pretty cool. So I'm doing stuff for the Apple, well, I never remember the website, Apple / wait a sec, I have the Zoom thing, apple.com/2030. Am I that lucky? Yes, I'm that lucky. Yeah, so we're working on stuff for like carbon footprint offsetting and carbon neutrality by 2030. So I'm in the organization that's working on this stuff, and we're using Elixir for quite a few things. That's pretty cool. So what are we talking about today? Before we start, one thing is that I'm gonna have time to answer all your questions if you want at the end. But if you have any questions about what we're talking about, so if you see some code that has something where you wanna like ask questions about it, please interrupt. I don't mind at all. I'm usually very happy to be interrupted as long as I can answer something when you have a question. So. Cool. So what are we talking about? We're talking about asynchronous. One last thing. There's a lot of text in these live books that I'm not going to read, and you're very welcome to not read it either, because otherwise it's gonna be very confusing to read this and hear me speak in the background. But the idea is that in 40, 35 minutes or whatever we have, I'm not going to be able to do too much clearly and like to go into too much detail on any topic really. So what I'm going to do is I'm going to give a big overview of all the, from the bottom up of all the options to do asynchronous processing in Elixir, asynchronous computation in Elixir. And then in a few days, because I need to upload this somewhere, I'll give you all this access to this live book so that you can actually go and read essentially this presentation, but in the comfort of your own home and the time that you want. You can play around with the examples and all of that. So hopefully that's gonna be nice. So that's why there's a lot of text here. So when I was preparing the presentation, I just wrote it down since I was doing that anyways. So what are we talking about? We're talking about asynchronous processing in Elixir. Elixir is a really well-suited language for doing this sort of thing. And first of all, just a couple of kind of basic concepts and definitions. First one is, what is asynchronous computation? Asynchronous computation in general is, we call asynchronous computation something that doesn't happen in the main flow of your program or in the root process that's running your program. So anything that's your program is running on the side is asynchronous, right? Sometimes this asynchronous computation happens concurrently, and sometimes it happens in parallel. So let's talk about what those two terms mean, and then we can kind of get into looking at a little bit more code. So concurrency and parallelism are sibling concepts. Concurrency generally refers to when a program executes different instructions interleaving, or like executes different procedures or functions interleaving them with each other. So you can have a concurrent program that executes on a single core. So for example, if you run an Erlang program on a single core, it's still going to be a concurrent program. You're still going to have multiple processes. It's just that they're a sequence of instructions, just that the instructions are interleaved between each other. And a parallel program instead is essentially the same thing, but the instructions are actually happening at the same time. So you can only achieve parallelism when you have more than one CPU, more than one processing unit. If you only have one CPU, you can only achieve concurrency. The nice thing is that you really almost never ever have to worry about concurrency versus parallelism, because we always write programs in the same way, in Elixir at least, because the beam provides an abstraction over the actual infrastructure that you're running, or the actual machine that you're running your code on. So the code is always going to look parallel to you, and you're always going to write code to deal with parallelism, even if you run it on a single core and the program is actually concurrent. Okay, so that's out of the way. If you have any questions, just a reminder to interrupt. And let's go to the next live book, which is Processes Basics. Okay, there's a way to erase outputs. There you go. Yeah, this one is a setup. We can run it. Okay, so I don't know if, by the way, everybody is familiar with live books. I kind of thought so, because this is all the rage at the moment. But if you are not familiar with live books, they're just like Jupyter notebooks if you use them in Python. But if you're familiar with that, they're the same thing. Essentially, it's like a markdown document where I can execute Elixir code. I have little snippets of code and I can evaluate them. So that's what we're gonna play around with. So let's start with spawning processes. So the basic, the real foundational knowledge we need to have is how to create different processes and have processes talk to each other. That's the foundation of asynchronous computation, the foundation of concurrency and parallelism, and everything like that in Elixir and Erlang. So as you know, when I'm executing an Elixir program, it's executing at least one process, and that process can create other spawn, that's the word that we use, it can spawn other processes, right? So the most basic operation is to spawn. Spawn, you can see it here, it takes a function, it can take an anonymous function, and it executes some code. So in this case, the function is just sleeping for 2 seconds, and then it's printing something to the terminal. So we spawn this function, and then we print something else that says just spawn the process. So if I try to run this, we're going to see the first thing that gets printed is just spawn the process. Let's wait a bit, which is this line. So it spawned the process in the background, and the process started executing right away. So process sleep, it started executing, so it started to sleep for 2 seconds. Then it goes right here, it prints this line, and then after 2 seconds, as you saw, it printed the line, finished the expansive computation. There you go. So this is just the basic of spawning a process. So it happens in the background. You can do other stuff while the process is running. And the process dies right when the function returns, right? Finishes execution, or if there's an error, like a raise or an exit. So that's a basic. Now we know how to create another process, but how do we actually have processes talk to each other? So the way that Erlang does that is through sending and receiving messages. And the reason we're looking at this is that you rarely have to do this stuff by yourself, but this is a bottom-up asynchronous computation kind of talk, right? So we're going really from, like, this is how everything we're going to talk about is implemented under the hood in some way or form with varying degrees of complexity, right? But this is like the foundations are these. So to have processes talk to each other, we send and receive messages. So these are the two primitive operations. The send operation is asynchronous. So you can send a message, and a message is any Elixir/Erlang term. And you can, if your process calls send, it can send a message to another process. So as you can see, this is how you call the send function. So you say send to a PID, that's, oops, nope, sorry. So you send it to a PID, that's the destination, and you send any message you want. Sending is asynchronous, which is very important, which means that when you send a message, you have no idea if or when it's going to be delivered to the destination. And this is important not for this particular talk, but it's important for the semantics of how message passing works, because it makes it then very easy to scale this to multiple nodes, because you don't really have any acknowledgement that the message has been delivered. So you send a message and then your process goes on about its day. The other primitive is receiving, and with receive you can actually receive messages on the other end. Receiving is blocking, and it takes, meaning that it waits until there is a message in the process that gets to the process that's receiving, or if there's a message already waiting in the process's mailbox. So as long as this idea of mailbox, which is just a mailbox of processes, like a queue of processes, of messages, a mailbox of messages, a queue of messages. You can have multiple receive, like case and other things in Elixir takes patterns. So for example, here, this is going to match every message, but I could be more specific, and I could say, oh, if the ping message arrives, then do something else, right? So and receive is going to block until a message that matches any of these patterns arrives. So let's say that we have we spawn this process. What is this? We use the spawn function that we saw before. We use an anonymous function, and we receive, and then we wait until a message arrives. If I spawn this process, it's just going to return the PID of the process, and that's not really going to do anything else. It's just this process is going to wait forever until I kill it or it receives a message. So if I now go here, and the main process of the livebook, so the process that's executing all this code, sends a message to this process, we're going to see that the send call returns whatever I sent. It's just not very useful. It's just it needs to return something. So and then you get this printed. So it means that the process received that message. If I check whether the process is alive or not now, it's going to say, no, it's not alive, because it received the message, it printed this instruction, and it finished. If you want, I can show you. No, this I can't show you. Sorry, I wanted to show you that if I call process alive before sending, it's going to say true, but like it's not like how livebook works. If I execute this cell, it's going to execute all of them before. So anyways, you'll trust me on that. I can do it here. If I say process.alive, it's going to say true. And then I executed all this stuff, and it's going to print something and then return false. Receive also supports a timeout. That's really important, because you really almost never want to have something like this where you just receive a block from messages and just wait. Because if there's a bug in your code, for example, if this is not message, but it's just like, something like this, where there's a pattern and this message never arrives, then this process is just going to be blocked, and it's never going to actually consume the message you want to consume. Right. So what Elixir provides for this is the after clause that you can pass to receive, which takes a timeout. And essentially, if no message is received within the timeout, here it's in milliseconds, right? So here it's 5 seconds. Then it's going to execute some code that can get out of the receive, basically. And we can see this in action. If I just spawn this process, it's going to wait 5 seconds, no message. I'm not sending any message to it. So after 5 seconds, it's going to say timeout, no messages, executing this code. So 3 primitives: send, receive, and spawn. And with this, there's only maybe one more that we need, which would be a linking process, which we're not going to go through because it's not really necessary for what we're doing. But with those 3 that we talked about plus link, you can build almost everything that's built in OTP. It's just a matter of then abstractions and layers of abstractions. But with the tools that we have, we can already build a pretty cool parallel map thing. So in this, let's look at this code for 1 second. And parallel mapping is, I'm kind of assuming that everybody's familiar with what that is, but it's like mapping where every element is mapped in parallel. You know what mapping is, because if you're writing Elixir, everybody is writing maps all day long, or like map operations. So parallel mapping in parallel is just what it sounds like. So how do I implement the parallel mapping function? Well, what I do is, what we can do is that we have an enumerable of elements, and we have a function that we want to map over them, right? So what I'm going to do, I'm going to go through all the elements first, and I'm going to spawn a process for every element. So as you see, I'm mapping over the whole enumerable, and for every element, I'm spawning a function. And what the function is doing is calculating the mapped element. Actually, maybe this is better if I call it like this. So it calculates the mapped element, and then it sends it back to the parent, tagging it with the PID of the new process that I just spawned. I have to calculate the PID of the parent here because so that it's a closure, so that I have it available here, because in here the call to self returns the PID of this function, not of the parent. So now I mapped over all the elements. I have a bunch of PIDs, and I return them because this is a map. So now I have this list of PIDs, right? So these functions are executing in parallel now, right? For every element. So what I need to do now is just collect the results, basically. So what I do is I have this list of PIDs. I just map over those PIDs, and for every PID I receive, and I wait for the message that PID is going to send me. So this process is going to send me, it's going to send the parent a message that looks like the PID and the map element. And I'm going to have one of these messages for every PID, right? So what I'm doing here is exactly that. I say, okay, for every PID, receive, this is like I'm matching that this is the exact value of PID plus mapped element. And I do not have after here to make the code just a little bit smaller, but it would be a good idea to like have a timeout here as well. But and then I'm just returning the mapped element that the process sent me. So if I do this now, let's comment this out 1 second. If I run this, it's like we can see that it works. Well, okay, yeah, it's saying that the assertion is true. So that 1, 2, 3, if I parallel map the function that adds 1, is going to be equals to 2, 3, 4. You can see this here if I do this, 2, 3, 4. And even cooler, a way to see that this is actually parallel is that let's actually do this. Look at this. If I do in a map, and for all of these numbers, I sleep for that many milliseconds. So for example, I map for, I sleep first for 1,000 seconds, then for 1,000 milliseconds, 500 milliseconds, 10 milliseconds. And if I sleep now, this is going to take, well, roughly 1.5 seconds, right? And this is actually going to be easier if I do this. Let's say this working, it's going to take roughly 3 seconds, right? Because it does sleeps for 1 second, then 1 second, then 1 second. If I do the same thing, but I change this to our parallel now, it's going to take roughly 1 second. And as you can see, I mean, I hope that you could see that this is like quite, it was faster. It took 1 second. It's executing this stuff in parallel. This is one of my favorite programs ever. It's terrible. Like this has so many bugs that like, yeah, I can't even like begin to tell you how many are there. But it really does show you that, like, I mean, everything that you put on top of this is just like bells and whistles to make it very resilient and to make like maybe more generic, blah, 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 like to have like more functionality on top of this. But this is it, right? This is like, it shows you how powerful these features are to build these concurrent programs. Cool. So this was the basics. Any questions on this code? You're going to have time to play with it as much as you want when I will give you this library. So let's move on. Let's move on to one of my favorite things in the world, which is, I need to find it because there's no session here. Tasks. Open. Okay. Okay, so let's talk about tasks. Tasks are, so we talked about processes and these primitives. You really don't ever use those primitives in the day-to-day code that you're writing because they are a little bit too low level, I would say. So it's good to know what they are and what they do, but it's almost, there's almost always a better abstraction for real world problems, I would say. And one of those abstractions is tasks. So tasks are processes that kind of like take care of a bunch of stuff for you. So you can spawn them in the same way that you can spawn processes using task.async. And then you can wait for the result that they return by using task.await. So as you can see, there's no sending, there's no receiving. It does all of that for you, plus a lot more. So if I run this little program here, it's gonna start the task, it's gonna sleep. So first of all, it prints running task. No, sorry. Yes, it prints running task, then the task starts executing and sleeps for 1,000 milliseconds, and then it prints this and it returns a random value. And as you can see, the return value of this is the return value of this task.await call, and it returns a random value. If I run it again, it's going to sleep for a second, return a random value. So it is a little bit simpler already than processes. And the cool thing is what happens is that a lot of the bugs that we had before, where like we're not, for example, we're not waiting don't have timeouts, or we're not really checking for errors or stuff like that. They're taking like tasks take care of that for you. So for example, if I await, I use tasks that await in a passive timeout, which is by default is 5,000 milliseconds, it's 5 seconds. Here I'm passing half a second. If I do this now, it's gonna exit and it's gonna say, so this call is gonna exit and it's gonna say, oh, it didn't return in time. It still prints this because it's not killing the task. You have to do something different with that, but it gets you an idea. A really cool thing that you can do with tasks. So tasks are really good for a lot of use cases. One of them that I like a lot is to execute computations that are bounded in time, meaning that you want to give some function a time slot to execute. And if it doesn't execute in the time slot, you want to stop it. You can do for a lot of things. You can do that by just providing a timeout. So imagine, for example, an HTTP request. Usually there's an option you can pass to the HTTP client that says, okay, timeout, and it's gonna like take care of the timeout for you. A bunch of times you don't have the possibility because the library doesn't implement timeouts or whatever, right? What you can do is you can wrap the computation in a task. So what I'm doing here is I'm saying, okay, let's start this task, it sleeps for a second, then prints something, returns a random number, is the same as before. And then instead of using async, I use task.yield. And what it is going to do is going to wait for 500 milliseconds, and then it's going to return a result. Well, it's going to return the result if the task returns one, or it's going to return nil if the task doesn't return within the timeout that I pass here, right? So if I execute this code, you can see that like the task.yield call return nil, and then the task finished after, right? And this is like a really cool pattern that you can do in Elixir, which is that you can, if this returns nil, you can essentially say or shut down the task. And this is exactly what I was talking about when I said, okay, you have a bounded computation that can only take 500 milliseconds and it can't take more. And if I run this now, you can see that it returns nil, but it doesn't print. Here it printed the expensive computation is done because this didn't complete in 500 milliseconds, but then it's still executed. We didn't stop it, right? What we did here is that we waited for 500 milliseconds and then we actually stopped it. And you can see that there's nothing gets printed. This line doesn't get printed, especially, right? And with already so this is already like a lot. It might seem very similar to what we did before with processes, but it's already a lot more than what we can do with just processes, because it takes care of a lot of corner cases and a lot of resilience and fault tolerance and error cases stuff for you. Task also provides the function that I think is the most underrated function in the whole Elixir standard library, which is like a very super useful. I love it, which is task.Basingstream. So if you've used that, it's a quite a kind of tiny function, but it's very generic and it's very powerful. So what it does is it takes an enumerable, so any stream, enumerable list, anything like that, and a function, and it maps the function over that enumerable in parallel. So it's exactly what we did before, right? So it's here it's taking like a list of timeouts, what we did before again. It's sleeping for the timeouts, and then it's like printing something, and then it's returning the timeout, right? And then I'm just converting, and it returns a stream. And I just run this, convert it to a list, and it's that you can see that it like the 100 milliseconds runs first, then the 200, then the 400, as we expect, and then it returns them in order. So the first one, it wraps them in an okay tuple. That's why you see this okay thing, but it's just returning like 200, 100, 400. I could just do this to show you. It returns 400, 200, 800 now. So it's really similar to what we did before. The super cool thing, well, first of all, is that it takes care of a bunch of error cases again. I'm going to stop saying that, but all of these functions do that. And then another very cool feature is that it takes a stream and it returns a stream, which is a very flexible API in Elixir, because it allows you to pass lazy streams to these, or infinite streams to these, and it returns potentially infinite streams, lazy streams that you compute in parallel, right? So until you do something like enum.list, nothing happens, and the stream could be infinite, and you could just compute as much as you need of it, and so on and so on. So it's very flexible. The other super cool thing is this: what if in our previous parallel map implementation, we wanted to parallel map over a list of 1 billion items, what would happen? We would spawn 1 billion processes, right? One process per item. That's not gonna work, right? As much as we like to say, oh, Elixir processes are lightweight, this is amazing. Yeah, they're lightweight, but not lightweight that you can spawn 1 billion, or like, well, you know, say 10 billion, say 100 billion, like, you know, you're never gonna be able to, like, it's never gonna scale to any number of items in the incoming stream, right? So what Task Async Stream provides to fix that is that it processes the stream here with a bounded number of processes. So it has this, it calls it maximum concurrency. So it has kind of like a pool of processes that it uses to do the parallel computation. You can control this number through this max concurrency option. It's what allows you to, and it's perfect because it uses a predictable amount of resources, right? So that's fantastic. So I can give this list with 1 million items, and I say like, okay, use 10 processes to churn through it, right? So I can control the parallelism exactly and independently from the size of the list, right? And that's really huge because, for example, imagine that your list of parallel operations that you want to do is make HTTP requests. There's a very low number of there's a very low diminishing return when you start to parallelize HTTP requests, right? I can do 100 in parallel, that's better than 1. But if I do like 10,000 in parallel, they're just going to fight for resources, right? So being able to control that level of concurrency is fantastic, right? And it's built in, and it works with the infinite streams and all of that stuff. So you can, for example, say, okay, process this infinite stream in parallel using 10 processes at a time, maximum 10 processes at a time. So that's really fantastic. Okay, so tasks. When do you? So this kind of overview. That's most of what tasks do. So it's like a very thin layer of abstraction on top of processes. But I would almost never use straight processes by themselves. I would, if I need the functionality of basic processes, I would always go for tasks because they, kind of implement a lot of error handling for you, and they provide stuff like Basingstream, which is fantastic, in my opinion. So when to use tasks? There's just a few examples. For example, you have a controller like in a web application that receives a request and wants to execute like a couple of HTTP requests to other services in your microservice architecture or whatever. You can do the requests in parallel by spinning up like a few tasks for each, and then you can collect the results at the end and you can parallelize that. If you need parallel mapping, never implement it yourself like we did because that's full bugs. Use something like Task Async Stream. Tasks are really good if you want to, as I said, perform a computation that's limited and you want to give it a limited amount of time and then shut it down if it doesn't complete in time. And they're also very useful to spawn computations in the background that you don't care about, like for side effects, for example. So if you want to log something in the background, there's this task.start function that just starts the task and like doesn't care about it, doesn't monitor it, it doesn't like, keep an eye on it, it just like throws it off in the background. So those are really good use cases. There's a bunch of tips here that I think are too low level to talk about here, but you're gonna be able to read through this when I'll publish these live books. One of them, I'm not really gonna talk about it, but one thing I wanna mention is that now we're gonna move over to like more complex abstractions for parallel processing. Task Async Stream goes a very, very long way. Like a lot of the time I went back to code that coworkers wrote, and like they built these like, big abstractions using tools like GenStage or Flow and everything to do these like kind of parallel computations and stuff like that. Task Async Stream very often is a very, very easy and approachable solution to do this sort of parallel mapping because it provides everything you want. It consumes streams, it produces streams, and it's like uses a bounded number of resources. So really good tool to know. Any questions on tasks while I slowly move over to GenStage?
Yeah, we have a few in the chat. I can read them.
Nice. Okay, I open the chat now.
So why does task.yield not shut down implicitly? So instead
why that task.yield doesn't shut down? Well, the reason is that sometimes you just might want to check if the computation is ready and wait for a given amount of time. And if it's not, like, do something else rather than shut down the task, right? So if it would also shut down the task, it would limit your just ability to choose, right? So the pattern of, like, yielding and then shutting down the task if it doesn't return in time, it's just like one more function call, and it gives you the ability, like, it gives those functions different rules. I think that's all.
Okay, makes sense. The next question is, task async runs in parallel. Is the order guaranteed for the results when you do task async?
Yes, that's a really good question. I can go back. So this is very interesting stuff. So I'd rather spend a little bit more time on this and, like, not finish everything than. Let me go back. Oh my God, tasks. So this is one of the practical tips was this. So if I run this, yes, it guarantees the order. And you might be thinking, oh, but if it guarantees the order, then it's gonna have, like, it's not really gonna use the 10 process all the time, because it needs to, for example, if there's a very slow element, before freeing up processes to compute further elements, it needs to wait for that if they have to be kept in order. So that's true. And that is why there is also, you can pass an option, which is ordered false. And I have an example here that you can run. If you say ordered false, it's not going to care about we're going to return the results as soon as they finish computing. So if it's the same code as before, I'm just saying ordered false, basically. So now it's like sleeps for 100, sleep for 200, sleep for 400, and then it returns them in the order, because that's the order they were computed in. So ordered false is very useful. It's like a performance optimization. By default, it's true. But as a performance optimization, if you don't care about ordering, for example, you're doing this for side effects, but you don't care about ordering, or you are collecting these results into, like, a map, or, like, into an unordered data structure, then you don't really care about ordering, right? So in those cases, using ordered false is going to be faster, probably.
Okay, I think there's a question on process ID. So why a process ID has 3 numbers, and why the first and the third number are always 0?
Good question. The first number is the node, I think. I'm like 95% sure. So if the first number is always 0, because you're always running probably on your own node. But if you were to spawn a process on another node, it would return the PID of the process on that node, not your own node, and then the numbers would look different. That's
so every section represents something.
Yes. Is the value returned by a task a PID that I can use to send a message? Yes, it's not a PID, it's a struct. Well, we can really easily look at it too. If I just, let's comment this out, it's the easiest thing. So it's a struct, as you can see, that has a PID inside. The struct is public, so you can use the PID field, and it also has some other things that are used internally by tasks. The ref is what is used to actually, like, monitor the task if all of that. So, but it has a PID that you can send messages to. Yes. What is the benefit of using task async? If you keep ordered true, async stream, I assuming, and the benefit is of using task async stream with ordered true. I assume as opposed to just a enum map, for example. If that's the case, it's because you want to execute those in parallel. So even if it's ordered, you still, for example, if you have max concurrency 10, you're going to process 10 elements at a time instead of 1 at a time, even if they're ordered. So it's just going to collect the results in order, but it's going to do the computations and you always have to think about computations that are expensive. Otherwise, it's not worth it. If you're doing, like, +1, there's no point in doing it in parallel, right? But if you're doing a IO bound operations, for example, you're doing HTTP requests, where an HTTP request could take 100 milliseconds, 200 milliseconds, then doing 10 is going to take roughly 200 milliseconds anyways, but doing them in sequentially is going to take 2 seconds instead. That's usually why you want to do that, even if the order is true. And what is the third 0 in PID? Good question. I don't know. I know the first one is the node. The third one, I have no idea. Something internal to Erlang. I don't know. usually you don't really have to care about what the PID is, like a dynamic value, so you don't really have to care about what the number is. But good question. We'll go learn that. Cool. This was thanks for the questions. It was great. And if you have other questions, the chat works fantastic. I'm gonna keep an eye on it. So, and I know that we're running late already. So what happens when you have fun? Okie dokie. So let's go through. Let's go through GenStage. Well, let's try to see what we can do. So GenStage is a library, and it's an abstraction over processing multiple. It's an instruction to build pipelines of stages that process data in parallel. So it's a library that's maintained by the Elixir core team, and the idea is that essentially you have something that generates events, whatever an event is, and then you feed those events through a pipeline of stages with different topologies. And these stages each have roles and perform computations, and you can hook them up together, and so on and so on. It's going to be easier when I show you. GenStage, first of all, is an OTP behavior similar to GenServer and or GenStateM or something. And one call out, why are we not talking about GenServer? You might be asking. Because it's kind of not asynchronous processing in Elixir. Like GenServer is more of an abstraction on stateful processes. So you don't really use a GenServer. Generally, you don't necessarily use a GenServer to process data in parallel. You usually use it to keep state, or to isolate some computation in an isolate failure and stuff like that. And instead, tools like tasks and GenStage and Flow that and Broadway that we can talk about. They are more for processing data. So GenStage, it has this. Okay, this is what a stage looks like. As I said, it's like use GenStage like you would do use GenServer. You have some callbacks. It really looks similar to something like GenServer or GenStateM. You have different stage types. You can have 3. You can have producer stages, which are the stages that produce events. You can have producer-consumer stages, which do both, like they get events from producers and then produce events for consumers. So it's easier to visualize this, I think. And then you have consumer stages, just ingest events. So this is what a GenStage pipeline could look like. You have a producer, you can have like multiple of the same producer-consumer, then you can have another producer-consumer, so on and so on, until you end up in a consumer. You can only have one producer, one consumer, as many producer consumers in between. And you can imagine data flowing through this pipeline. That's what the GenStage is doing. Why is GenStage cool? GenStage is cool because of this concept of demand. So GenStage pipelines we say that they are demand driven. So the pipelines don't really flow. They don't really flow this way that I drew here, where the events start from the producer and go all the way to the consumer. What actually happens is that the pipeline, the flow of the events starts from the consumer, or like the pipeline operations start from the consumer, because the consumer start to send demand upstream. This is a terminology we use. So essentially the consumer says, okay, I can process this number of events. This is what we call demand. And then it sends it upstream to the parts before in the pipeline, right? So it's going to say the producer consumer. Here is a better, simpler drawing maybe, where the consumer says, okay, I'm ready to the, right, sorry, the lady told the recording stop, that's why I stopped talking. But then she said the recording in progress, so I think we're good. So the consumer sends the demand upstream and tells the producer consumer, in this case, hey, I'm ready to receive events, and the producer consumer sends demand upstream to the producer and says, hey, I'm also ready to receive event, and the demand flows upstream. And only when the producer receives demand, then it's going to produce events. And you're going to say, like, why all this crap, like this is complexity here? And the reason for this is that it provides built-in back pressure in these pipelines. Back pressure meaning that like the events will flow through this pipeline only as fast as the pipeline can consume them. So if there's a slower stage in the pipeline, it's going to slow down. It's not going to produce unwanted events in the producer that are going to accumulate in the producer. You can it drives a pipeline where events flow very kind of precisely based on the capacity of the pipeline. So that's what demand is. And this is the biggest feature of GenStage, in my opinion. We can kind of skim through the code a little bit. This is the code of the producer. In this case, it's The only callback that it needs to implement is handle demand, where it's exactly essentially this. It's like someone is saying, hey, I'm ready for demand. So what do? You produce some events. And in this case, we are just sleeping for a bit to simulate thinking. And then it's just generating random bytes of random binaries of random bytes, as many as the demand. Demand is a number here. So as many as the consumer asked. So if I run this, it's just going to compile it, it doesn't do anything. Well, we can hook up a consumer to it. And this consumer is implementing a handle events callback as opposed to the handle demand callback, and it gets a bunch of binaries and just prints them. Compile this too. And the way that we wired this up is that first of all, we start the producer, we start a couple of consumers, and then since the demand flows upstream, that's the way that we hook up the pipeline. So we hook up the last consumer to the producer, then we hook up the other consumer to the producer as well with this sync subscribe call. So you can have this subscription flowing from consumer to producer. And then the producer is going to start producing events. And this code is just shutting them down after 10 seconds so that it doesn't go nuts. If I run this, it's going to say, okay, ready, set, go, because that's what I printed here. And here's the first batch of events. And then another batch of events is going to be printed. And these are just random binaries, right? And then another batch of events and so on and so on. So you can see the events kind of flow through the pipeline as fast as they can be consumed. Which is very cool. The producer consumer is not very interesting. It's exactly what it sounds like. It does both roles. It fills both roles. It also implements the handle events callback, as you saw. If you saw here, there you go. You can this argument here is the events that we return from the callback, and a consumer just never returns events. That's the only difference. A producer consumer can return events. So what it is doing is that it's just hashing them and returning the events with the hash. So it's just really not very interesting. But when you hook all of this up again, you're going to see that this does a little bit. It does it similarly, where it says like, okay, the hash is now here. So it's the events now are flowing through the whole pipeline. And the last thing I want to talk about the GenStage. So yes, the last thing to talk about GenStage when talking about GenStage is dispatching, which is what lets you build weird topologies of the stages. And dispatching is kind of how a producer sends events to the consumers. And by default, it's the dispatcher is the most intuitive one, which is called the demand dispatcher, which is essentially gives the events to the consumer that has the highest demand. So if you think about it, that's just saying, okay, I'm going to send the events to whatever consumer is freer, whatever consumer can handle more events, which makes sense because it's probably the fastest consumer at that point, or like the consumer that has more bandwidth. And you also have other dispatchers that you can hook up. So for example, a broadcast dispatcher is going to broadcast to all consumers, which is useful when you want to send copies of events around. Like you want to say, oh, a consumer for logging them, a consumer for uploading them somewhere, you can just broadcast to them. Partition dispatcher is also very, very cool because it's a dispatcher that dispatches events based on partitions, always to the same, based on hashing, essentially, always to the same consumer. So you can implement like more complex strategies where your consumers have more state and they're always consuming the same events and so on and so on. So this was a really quick overview. I really had to run through this of GenStage, but that's why I built the live book. I'm very proud of myself right now because now you can go in and you can read all of this, which is fantastic. And the more fantastic even thing is that we are out of time and I still haven't talked about Flow or Broadway. So if you want, I can like really take 2 minutes and I just give you the high level overview. Those are talks by themselves. So, I mean, there's only so much we can talk about. I generally prefer to like build a foundation that then lets you understand how, things are built on top. So if you want, I can give like a super quick, even just without slides, let's just do like 1 minute overview of what Flow and Broadway are. And then you're going to have access to this and there's live books for both. So you can step through. So if that's fine, I'll do that. So GenStage is this kind of like, we started from processes and then tasks and then GenStage, and then GenStage is a very high level abstraction, but it's still a low level compared to Broadway and Flow. So GenStage is this abstraction that lets you build these data pipelines. And flow, and then it kind of branches into two different abstractions, which are flow and Broadway. Flow is an abstraction that aims at essentially providing the same API that enum and stream do, but for processing those things in parallel. So it's kind of task async stream on steroids. So it lets you do like really cool MapReduce flows on data in parallel, and it lets you partition data and reduce it in parallel and merge it after, and it lets you set like windows on the data so that you can process infinite streams of data. So it's kind of an abstraction built on top of GenStage that looks like enum and like stream. So you can do like map, reduce, flat map, take every, like all the functions that you're used to in enum and in stream, but in parallel with like this very cool complex flows of data. So the ideal use case for flow is I have like MapReduce algorithms. That's kind of the best things that I can think of to execute this stuff in parallel. So that's one direction where we're taking GenStage and we're saying, okay, how do we use and it's built on top of GenStage. So you have this GenStage is what powers this parallelism and this, the back pressure mechanisms that are in flow as well. And flow is the answer to the question, okay, how do we take GenStage and make it process just streams simply, right? Instead of building GenStage pipelines. So that's what it does for you. And then there's another abstraction that this kind of spins off of forks off of GenStage, which is Broadway. And Broadway is a very simple way to build data processing pipelines where you can hook up a Broadway pipeline to anything at this point. You can hook it up to RabbitMQ, to Kafka, to SQS, to Cloud PubSub, to Redis, to anything that produces events, to any like message queue, anything like that. And then you define very, very simple call and in a very declarative way. So I actually can show you because I think that's the coolest thing about Broadway is that you can declare a Broadway pipe. This is a Broadway pipeline, that's all. And this one is saying like, okay, connect to RabbitMQ and process the events with this concurrency. So you can set up all this stuff very declaratively where you say, okay, consume events from this queue and use this concurrency, blah, blah, blah. And then you just have callbacks that execute when you get events. So it's kind of like, it's similar to what GenStage does, but very, very, very trimmed down to be much more declarative and to have like a pluggable architecture where you can have different producers that Broadway provides for like stuff like RabbitMQ, SQS, or Kafka or whatever, and it lets you build like very easy event pipelines like this. And at my previous job, we had like this just an anecdote, and then I finished. At my previous job, we had a event source system where we had about 100 services maybe, and all of them were publishing and consuming events. And we had like millions of events every day on RabbitMQ. And all of these services, all of them used Broadway, and all of them was essentially very simple services that would like consume some events through Broadway and process them, and then maybe publish them at the other end to publish different events to RabbitMQ. So that's like kind of a perfect use case for Broadway because it's it really lets you just define like with very concise code, lets you define ways to process data coming out of different places. So it's a very and you can play around with this in this live book. There's a bunch of code, and you can it works, as you can see. You're left around RabbitMQ, but I'll add some information how to do that.